or evening, depending on where you are. This is the second of a 4-webinar series on modeling flood sediment with Flow2D. And this is the second of 4. So let me, last week we did conventional sediment transport. And so this week we're doing Mudflow, and then next week we're going to do a webinar on Mudflow sediment yield, and that is how to provide the sediment supply to mudflows. And then finally we'll wrap it up with a webinar on two-phase flows for mudflows and tailings dam breaches. Now let me just make a mention, a little bit of background information here, is that Flow2D actually started as a mudflow model. It was funded by FEMA in 1988-89, and I provided the initial program executable to FEMA for the city of Telluride in Colorado, and it was called Mudflow, believe it or not, before we changed it to Flow2D in the late 90s. So this model has been around. It was odd that we started it as a mudflow model because all the other models that are doing debris flows or mud flows, they are started as flood models, and they've been Johnny-come-latelys because only recently have you seen some other models doing mud and debris flows. We've been doing it for essentially 35 years now. So, and I'll talk a little bit more about that in a minute. The approach in Flow2D is a volumetric conservation approach, and the objective is to match the potential sediment supply volume with the volume of the hydrograph that you're trying to model, and that might be a design hydrograph or maybe you're trying to replicate a given event that occurred in the past or something. So in doing this, my focus has always been that we're modeling a continuum where mudflow is part of an increasing sediment concentration from water all the way up to landslides. And I'll show you this table in a minute. The reality is that even though people like to refer to these as debris flows, I refer to them as mud flows. And the reason is because the fluid properties are what controls whether or not you're going to have a mud flow or a flooding event. It's not the debris. And the debris is not a very good descriptive name. So I use mud flow, mud floods, and so forth. The limitation of the model with mud flows is that there's no exchange with the bed sediment. That is, the mud flow can flow and then cease flowing and then remobilize, and it's tracking the sediment by grid element in terms of both the sediment and the water. So it calculates the concentration on the fly for every computational time step. Now, we've remedied this limitation to a certain degree with the two-phase flow new component, and I'll discuss that in the fourth webinar. The product of your simulations are going to be basically an area of inundation, and what you'll use out of that is the maximum hydraulics, and you'll try to create a worst case scenario for flow depths and an area of inundation. But again, there's a range of conditions that this applies to, so you have to be cognizant of that. So just a little bit review again, we went over this last week, that the concentration by volume that I talk about here is nothing more than the volume of the sediment divided by the total volume, which is the volume of the sediment plus the volume of the water. The bulking factor associated with a mud flow or mud flood is nothing more than 1/1 minus the concentration by volume. So if your concentration by volume is, again, on the order of 40 to 50%, say 50%, then 1 over 1 minus 0.5 is 2. And so you're essentially doubling the peak flow and doubling the volume in your event. And as I mentioned last week, no flood is clear water, obviously. And I discussed last week where I took a measurement while this flood was occurring of a bottle of sediment in the fluid and took it back to the lab. And most people would anticipate that this concentration is somewhere around 30 or 40 or 50%, when in reality it's very turbulent. It's mostly a water type of flooding, and it was about 22% concentration by volume. And the boulders that were rolling along the bed really don't make a significant portion of the volume. So you ignore those as part of the fluid matrix in this. But is this a mud flow? And the answer to that is no, it's not. It's a mud flood, and if you look at this graph here, it'd be down around at the lower end of the mud flow. So let's go through this for a second here. Less than about 20% concentration by volume is a water flood, and it's a conventional flooding with suspended load and bed load. Now, most of your sediment transport equations are really only based on flume and river studies up to about 10 to 11, 12% concentration by volume. So we're extending that a little bit, but indeed up to between 20, 25, 30%. You have a very fluid type of an event with all the particles they will rest on the bed when the fluid has ceased flowing. So this is important. The inhibited fall velocity of particles begins somewhere around 35 to 40% concentration by volume. And that's when you still will have a fluid on the surface. And if you allow the fluid to come to a stop, most of the sand and gravel will settle out, but not the fines. And the sand and gravel will still move as bed load. When you get to 40% and higher, you have a marked settling of gravels and cobbles, and mostly an even or uniform spreading on a horizontal surface. It's still a liquid surface, though, with two phases of fluid. That you can see that, and the waves will travel on the surface fairly easily. Finally, as you get to the upper end of what I consider to be still a flooding event, the flow mixes easily, shows fluid properties and deformation, spreads on a horizontal surface, but can maintain an inclined surface. That means that the yield stress and the cohesive qualities component of the flow is becoming more important. And you still have large particle boulders and cobble settling, but the waves that appear will very rapidly dissipate. Once you're above 45% concentration by volume, up to 55% concentration, and maybe a little higher, you have flows spreading on a level surface, but it'll maintain an inclined surface, and it'll be a very cohesive flow, and there'll be a little mixing, but mostly above that, you're going to have more of a plastic deformation, deformation under its own weight. It's still going to flow as a fluid, but it's not going to necessarily spread on a level surface. And finally, above 55 to 60% concentration by volume, you're going to have block sliding failure with internal deformation. So I'm going to show you some videos of this. Let's take a look at a few pictures here first. Most classic mud flows will evolve a more of a U-shaped channel, and the core of the flow will be only in the interior of the channel, and you'll have these shear zones evolving here that are very distinctive. Typically, there is a frontal wave associated with it, although the frontal wave may slow the the movement down a little bit until the peak catches up with it. The frontal wave doesn't play a significant role unless there's very little volume in the entire event. Play a significant role in the propagation and progression of the flow past the alluvial fan apex and on downstream. Now, just to give you some comparison with some other types of flow, this is a granular flow. This was in Utah. Now, this probably had some fines in the flood event, and the fluid itself was lubricating this flow, but the flow was principally rolling and um, through the collision of particles, and the collision of particles, like billiard balls, kept the momentum of the flow moving. So, you know, this type of flow is very rare, and although you could probably model it somewhat with Flow 2D, I'm mostly simulating fluidized events with this, but I wanted to show you what a granular flow, and these are, again, fairly infrequent. They're hard to find. You might look at a flow and say, oh, look, it's kind of a granular dispersive type of flow. But in reality, it was just surface washed, meaning that this is the same event here. And if you dig down underneath the event, you can see the actual mud flow type of event, and then subsequent flows over this during the recessional limb winnowed out all the fines and left a more coarse deposit or armored deposit on the surface. So I'm going to show a few movies now. The first one is what I would consider to be a fairly classic, or a mud flow anyway, where the peak discharge occurs near the frontal wave. The highest concentrations are in the frontal wave, and it creates self-containment levees, which are always a feature of a mud flow event. I'll turn off this sound. Bear with, there we go. Now this is kind of interesting because obviously these people are aware that this happens on occasion. They actually have like little sabo dam structures to try to reduce the impact. He hears it coming. I don't know how they were actually notified that this was going to occur, but clearly they've designed this channel so that it would do its job in containing this flow, except that it doesn't. Now you can see that this is fairly fluidized here, but it clearly is a mud flow because it's actually, the flow is ceasing as it hits a flatter slope, and it creates these containment levees, which then forces more of the flow downstream. She's very brave. I mean, I can't imagine that they must have this occur frequently enough that it that they're used to it by now, and they know it's not going to go up on their property very far, but it wouldn't take much more of a larger event to actually do some damage. Obviously, this vehicle here got displaced. So that's one, and I showed you that because you saw the peak or the frontal wave coming down. Essentially, the peak caught up to it right around in this area here, and then it created berms and stopped you know, flowing. So the next one I'm going to show you is a mud flood, what I would consider to be a mud flood. This is highly turbulent. Let me see if I need to do this. It worked. Let me shut this first and then redo it here. Yeah, here we go. So let me turn the sound off again if I can. Whoops, sorry about that. I can't get the screen up high enough to turn the sound. Here we go. Okay, sorry about that. Now I'm going to move it ahead a little bit because this is before the event. You'll see the event coming down now. So this has a pretty significant bouldery type of frontal wave, and you would be inclined to call this, I think, a debris flow. Watch these boulders get launched here. Now, right here, it shows a very bouldery type of frontal wave, but this is clearly, immediately a mud flood. And you can see that even though the boulders are getting pushed along in front, the peak has rapidly caught up with the frontal wave here, and now it's just a mud flood event. And this has the shear zone effect that I was mentioning before here, where the flow is in the core of this. And you saw the more U-shaped type of channel associated with this event, but I would suggest to you that this particular watershed must have this type of flood event occur very frequently because they've got this early warning system here in place. And they also have this, again, this Sabo dam type structure, which I'm not a big fan of. These Sabo dams may prevent some, for a mud flow event anyway, may prevent some of the scour of the bed of the channel, which can be the significant portion of the sediment loading in the system upstream. But the bottom line is that it really doesn't do anything except even out the slope, especially when you consider how much volume is in these events. So it's not really storing much sediment in the channel. It's just preventing the scour of the channel down. But once the channel is, as if you can sacrifice the channel itself in terms of confining the mud flow event, I would look towards other mitigation measures other than the Sabo Dam works in terms of trying to mitigate these events. Okay, so that there you get the idea with this one too. Now let me turn this one off. Now this third one I consider to be a classic mud flow event, and for this I've got the this is YouTube, so I'm going to give you the, I'm going to turn it on first here. Now this is a real classic mud flow event, and you may have seen this. I think this is in Switzerland, and I'll move it ahead a little bit for you. Here we go. It's interesting to think though that that car and the fencing was all there, and the shoreline, the banks were all ripped wrap, looking very nice. It looks like they've have some kind of internal structure here that they use to mitigate and contain the mud flow event, but it obviously didn't do that. Now, the reason I want to show you here is that this is a fairly uniform concentration. It's pretty high. It's probably on the order of 50%, somewhere between 45 and 50%. And the flow is not that deep here. It's fairly shallow. Yet look at how destructive this is being here. It's just pushing everything along. I would suggest to you that the flow depth here is less than a meter. What I wanted you to see was the nature of this mud flow form. Now you can see up here, way up at the top, that the mud flow is over bank over here. Watch this truck. This truck's going to move. It's on the street or whatever this is over here. I think it's a street, but you can see some of the boulders moving downstream. I think it's on the street over here, and this truck got trapped in it. And also a crane got trapped in this too, of some kind. And you'll see that in a moment in another view from downstream. I'm going to move this ahead just a little bit. So you can see this truck has gotten pin now in a different direction, and it's a little bit more fluid. So important to recognize that these kind of events don't all take place with a uniform kind of concentration throughout the entire event. It's probably entrained some more water, or the landslide, or whatever the source of this material was. It's gotten a little bit more fluid because more water is entering upstream. You can still see some boulders moving along on the other side over here. I'm gonna move this ahead just a little bit more for you, because you'll see that this entire, if you compare this picture with what took place right at the beginning, pretty amazing that the car, the fencing, and now the entire log mill here is collapsing. And of course the flow is a little bit deeper here too. Pretty superior footage. Okay, so let's go to the next location. This will start here in a second. Let's see where we are. Okay, so this is a little bit downstream. You can see here's this crane or shovel that was moving up and gets trapped somewhere. This is that house that the helicopter was landing near or behind. So this is a little bit further downstream. But you can see that this material that we've seen collapse from upstream is now moving into this area. It's really fascinating. Move it ahead a little bit here, and you'll see that it tears out this entire bin. A huge boulder just came over this wall. Okay, so finally, if we move down a little further downstream now too, you'll there's that house that you saw in the last picture. And what's interesting about this is that this is a fairly substantial structure with concrete pillars. It's pretty well pinned. You can see that as this bin comes down here, metal bin, slams into this, it jars this structure a little bit, but the structure doesn't collapse. See, it jars it again. I'm showing you this for a reason. Now watch this. Bang, it jars it again, and yet the structure is maintaining itself until now you see this debris or maybe roof or roof of a shed or something here has collapsed and is collecting some of the flow on the entrance to this. I only have a minute or so here left, but I'll move it ahead a little bit. Okay, so here comes some more debris from upstream that we saw in the previous one. It's collapsing this structure, bin shelter up here, and then watch what happens when this structure here. And again, you're only moving at about 2 or 3, maybe a meter or 2 per second. Okay, so the structure was in good shape, but the entire structure collapses. Pretty amazing stuff. Okay, so let me pause this now. Now I have one other short ones to show you so that you can distinguish between the mud flow and a more of a landslide type of nature of the event. And you can see here that this is just sliding along, tumbling, maybe rotating blocks inside, but there's no velocity distribution in this flow. So this is clearly, even though it's not a structured landslide off the hill slope itself, this is still more of a landslide event. When it stops flowing, you'll be able to walk on it. So there's no fluid deformation in this, and that's what I wanted for you to see in this one. And I don't think it's necessary to show you any more of that. So, okay, so let me go back to my presentation now. So I hope that was informative for you. So in this last movie, I showed you some tumbling blocks, plastic deformation, and it did create some natural levees to hold itself too, which is very evident in this first one and in the very first movie and in the last movie. Okay, so I want to show you now how these different types of events are actually being modeled in Flow 2D, and that is we're using a stress-strain relationship in order to incorporate into the equations of motion, the momentum equation and the continuity equation. And you can see that the shear stress is equal to the yield stress plus a viscous term, where this is a linear velocity distribution, and this is the viscosity. So if you didn't have a yield stress, then this would be Newtonian flow, and the shear stress would be equal to a coefficient times the rate of shear, or the vertical velocity distribution in this case. Now, if we add other higher order terms, where we take the rate of shear raised to the second or third order power here, then we're starting to incorporate turbulence. And this C coefficient here is a function of both turbulence and dispersive stress, meaning particle to particle contact. So if you model the flow only as a Bingham fluid here, then this is a laminar flow relationship here. So there's no turbulence in it. In order to have the turbulent terms be modeled, you have to have the higher order velocity distributions. So what this looks like is that if you have a Newtonian fluid here, and the slope is a linear relationship with so that the stress and rate of strain is a function of only the viscosity, which is this slope term here, then this is still a Newtonian fluid. If you have to overcome a yield stress in order to initiate motion, then it's called a Bingham fluid, but the slope term here is still linear, and this is what I just mentioned to you in the previous equation, is this Bingham fluid here. If you have a shear stress that begins to be nonlinear and rapidly increases with the rate of shear, that is the vertical velocity distribution here, to the second order or higher order terms here, then we're adding this component. This is referred to as a dilatant fluid, but this is what the Flow 2D model is based on, and we just use the second order, no higher order, third to fourth power terms here. Now, there is another one here that just says that with increasing shear stress, you go faster and faster and faster with very little increase in shear stress. That's a pseudoplastic term in which this becomes a negative contribution to the actual Bingham fluid. And you know, this is very rare. This is more like actually like plastics or plasmas or something like that. So the mud and debris and not the debris flow, my fault, mud and mud flood events are modeled in Flow 2D with that term. So what we need to do in order to model these is we need viscosity and yield stress as a function of sediment concentration. So in my PhD dissertation back in 1986, I actually collected the data in like 82 to 84. I went out to various locations in and around Colorado and collected some samples, brought them back to the lab, and these samples were all actual mud and debris flow deposits, mud flow deposits. And then I compare these with other researchers at the time that I was able to find. Now, there have been a lot of people who have done this since, This was just my original dissertation table, but I think it covers a lot of what you'll need in order to model mud and debris flows in the Flow 2D model. So what we have here is just a coefficient alpha, an exponent raised to a power beta, and a CV. Now you'll note that this is an exponential relationship, and all these other researchers found the same type of expression fit the data fairly well. And I did this on my own, and then later I found this data to match that. So it was just a curve fitting prospect, but other researchers have since done the same thing, and that's including the USGS up at the Cascades Volcanic Research Observatory in Vancouver, and the people out in the Swiss Federal Forest Institute in Zurich or wherever they are. All of these different researchers use the same relationship. And if you plot these where you have viscosity as a function of concentration, then you have these different plots here where you each one of these points here represents a fairly significant number of data points, because each one is based on a concentration. But in order to do this, you have to go back to this plot here and get a series of these plots, a series of these shear versus stress points in here. So you'll have your rotational viscometer operating at one speed, and then you'll crank up the speed, measure the shear stress, and you'll get these points on this curve that will lead to one point. So it'll take you like 10 measurements in order to get one of these points. So each one of these plots here represents, and each one of these curves represents about 100 data points. Now, what I would recommend to you, and what I'm going to talk about, is how you should select one of these and how to plot these in relationship to this data. In other words, I would try to fall within the bands of this data here so that you can do a fairly substantial, accurate job of modeling the mud flows. Now, the yield stress has the same relationships essentially, and you can see that there's some bands in here, and I made the band for you. I would try to probably stay within these dotted lines here, these dashed lines. So in order for you to select these mud flow parameters and use them in the Flow 2D model, please note that each basin is going to have geology and soils that are going to contribute to different viscosity and yield stress relationships as a function of concentration, primarily due to the concentration of fines, that is silts and clays, in the flow event. And so the clays play a major role in this. And the sand can also, fine sands may also create some different curves, because they break down the bonding in the clay so that the curves will be slightly different if you've got some clay in them. The very viscous mud flows that you saw pictures of there, though, the cobbles and the gravels and even the boulders are playing no role at all in terms of how the flow is progressing downstream. It's mostly the viscosity of the fluid itself. So there are two possible approaches to this. You can perform a laboratory analysis and get the viscosity and yield stress, or you can select the parameters from existing data. Now, if you want to do the lab work, it requires you to do a measurement of the viscosity, and you have to build or buy a viscometer. This is a picture, this is from my dissertation here, and this is what I designed this viscometer to do. This is rather time consuming, and you have to calibrate it with a known fluid, like glycerol, which is about as high as you can get, although today you could do it with maybe some asphalt or other types of high viscosity uh, samples, but you would have to have a commercial viscometer too, maybe alongside this, in order to get a some more highly viscous fluids to calibrate with. I did it with glycerol, which got me at the lower end of what a mud flood would be essentially, and then everything else was projected. Now, what's interesting is that you now can buy viscometers, whereas if you do your own viscometer, it's inexpensive, but it requires calibration and it's very time consuming. You can buy these viscometers, and Brookfield Amtech sells viscometers. The only trouble is they're expensive. I think this one is like $5,000 plus, and this one is from $5,000 to $9,000, something on that order. But if you go to Brookfield Amtech website, you can actually order these online. And they be very careful. You want slow speeds. If you build or buy a viscometer, your rotational speeds should be, the shear stress component should be the du dy, vertical velocity distribution, or the shear rate, should be on the order of what you see in the field. And that's on the order of 1/10 inverse seconds, or about 0.1 inverse seconds. So what you don't want to do is get a viscometer like this, or like the one that I built, and crank it up to 100 inverse seconds, or some higher rotational speed, because all you're going to do is have slippage in there. It's not good. And so what you want to do is actually create something that you're going to see. So if you had a vertical velocity distribution of 1 to 2 meters per second on the surface of the flow, then you could actually calculate that the vertical velocity distribution was something on the order of maybe 2 inverse seconds or 3 inverse seconds or something like that, depending on what you saw in your flood event occurring. If your flood event's coming down at 15 feet per second and it's 6 feet deep, you're going to be something on the order of maybe 5 or 6 to 10 inverse seconds. So that's very important. You want to make sure you get an actual viscosity measurement and not just slippage. So if you see some data that's published with rotational speeds on the order of 1,000 RPMs or something like that, you can toss it. Okay, so that's rheology. I welcome you, if you're going to do a very in-depth study of your own watershed, that you consider doing this viscometer analysis. Otherwise, it's possible to take a more simplified approach. That is, go out in the field, maybe collect some undisturbed deposits, note whether or not you've got berm or frontal berms where the flow has ceased, or lateral moraines, or something like that. If you get the undisturbed deposits, I would take the boulders and debris off the surface, dig down a little bit, and get what is actually in between the boulders and the cobbles, and take that back to your lab, clean it, dry it, burn off the organics, sieve the samples. Then analyze the behavior by starting with one concentration. And the way that you do that is you weigh the sample dry, and you add a certain amount of water to it, either by volume or by weight. You compute the concentration by weight. You can convert that to concentration by volume. And then you have 1 point in your viscosity versus yield stress behavior sample. However, if you do this for one that's if you're doing the laboratory approach. I would do this and then wet it, and then put it in like a maybe a small aquarium or in a tank or something, and slosh it around and see what you get in terms of that first table that I showed you, showing the different behavior for mud flows, mud floods, and water type flood events. And then given that, you can select which of the different samples that would more closely match your field conditions. So in other words, you take one of these samples here, one of these different um, research samples that either mine or one of the other researchers made, and take a given concentration by volume, say 40 or 45%, and calculate the viscosity and the yield stress for it. And what you're going to find is that compute this for one concentration, do a number of these different samples, then try using these different relationships for one inflow hydrograph and one sediment concentration. So say you did different samples for say 35% or 45% or something. So you would have different viscosities that might fall in this range right here. Then if you compute these for one concentration by volume, you might look and say, this sample has high viscosity and high yield stress. This sample has a relatively low viscosity and a low yield stress. It's going to behave more like water or a very turbulent mud flood. You could have a high viscosity and a low yield stress, which means that it's very viscous, but yet it doesn't withstand any shear stress before it starts moving. Then you could also have a low viscosity and high yield stress. Well, this is pretty unlikely. You're either going to have high yield stress and high viscosity or not, but I suppose that's another option for you. So in order to select these different mud flow parameters to use in your model, if you're not going to do the laboratory analysis, try several viscosity and yield stress relationships for one inflow hydrograph and one set of sediment concentrations, and see what impact you have on your area of inundation and maximum velocities. Now, there's a couple other parameters that you can select, but they're also hardwired into the model. Well, actually only one, but I'll show you two of these. If you look at, again, the shear stress as a function of yield stress, viscous stresses, and turbulent dispersive stresses, this viscous stress here, you could actually solve this for laminar flow, and there's a K factor that you could include as a coefficient in here. So for large viscosities in laminar or transitional flows, turbulence is very much suppressed. It's approaching laminar flow, and K, this value, this coefficient, becomes more important. Now, I have these resistance parameters for laminar flow, values of K, in here. This was based on some research that Woolheiser did. He was at Colorado State University when he was there, but he did this research in 1975. I came along in 1978, but he was there. He was a really tall, lanky guy. And he was doing a lot of analysis in the flume. And so he derived these different laminar flow coefficients. Now, what I did for you in the Flow 2D model is you can select these. This is the last parameter in line M of the sed.data file. However, if you enter K is equal to 0, this laminar flow resistance value will be automatically calculated from the N values that you're using in your model. So there's nothing you have to do. A typical N value or K value is about 2,500. That's what I typically use, is around 2,500. But again, if you just set this equal to 0, I've derived different, well, I use this and different N values for similar types of surfaces and calculated the laminar value for you. Now, there is also a dispersive stress coefficient that contributes to the shear stress relationship as for the higher order terms, and for the second order turbulent terms, the inertial impact from colliding sediment particles gives rise to this dispersive stress. So it's just the concept of having billiard balls rolling down a flume bouncing off of each other. So we have all the stresses now represented. We have cohesive stress giving rise to yield stress before it starts flowing along with more Coulomb type stresses. We have viscous stresses that results from the interaction of particles in their surrounding fluids. They tend to inhibit the fall velocity. We have commercial inertial impact, which also inhibits the fall velocity. And then we have the turbulent mixing, which keeps the particles in suspension and gives rise to this collision. So in order for the dispersive stress to occur, 3 conditions must be satisfied. Now, this is just for your edification. If you wanted more information on this, Pierre, Julian, and I had actually written a couple of papers on this back in the 80s. You need a high sediment concentration, something approaching around 50% concentration by volume. You also need large velocity gradients. So remember, I was telling you about a 10th inverse second. So you need to have the ability to have a nice vertical velocity profile. And then you need fairly large sediment particles. That's something on the order of 1% of the flow depth in order to have this billiard ball effect. And if you do this without going through all of the ways in which we derive this, if you take the concentration, and this is the laminar packing coefficient, I believe that's what it is. It's the laminar. Anyway, this is Bagnall's lambda value here. I've forgotten what it was. It was, anyway, and this is the flow depth in relationship to the particle size. We can compute a Manning's N dispersive coefficient as a function of a typical turbulent Manning's coefficient, so that you could use this in the model. So when we did this, and this is a little complicated, I'm not showing you any of the graphs and plots and data that we use to derive this, but if you derive this, what you see is that when you have a CV, a concentration by volume of 0, well, the dispersive stress component is 0 also, because there's no particles in it. When you get up around 50%, the relationship between the dispersive stress and the turbulent stress is on the order of 1-to-1. So about half of the loss of the momentum and energy in the flow is due to the particle collisions. That is the momentum being transferred from the core of the flow down to the bed by heat, about 50-50 turbulent versus dispersive impact of particles on the bed. Once you're above 55%, this rapidly goes to infinity, where once you're around 61%, you're essentially at a porosity of natural soil conditions. It's Bagnall's maximum concentration by volume for typical soils or natural ground. About the highest you can go and still have natural ground is around 74%. So somewhere, and if you have uniform spheres, the concentration by volume is 56%. So you can get a little bit higher than that, get up to around 60% concentration by volume, in which case the dispersive effect on the flow momentum is going to be like 4 times to 5 times that of the turbulent resistance to flow. So what I'm trying to say to you here is that this all makes sense. You start walking on ground around 40% porosity. You have to separate the particles in order to have fluid motion. So you're going to decrease this a little bit and get down between 55 and 60% concentration by volume. So if you see people talking about concentration by volumes of 74%, what they're doing is including some of the boulders in the flow, probably in their concentration, but the boulders aren't contributing to the flow motion and the fluid matrix. So I would leave the boulders out, in which case this can't be anywhere close to 70% concentration by volume. So I plotted this and made a relationship where the turbulent dispersive is a function of the turbulent dispersive or turbulent end value. So this is inherent. Now I embedded this in the model. So again, there's nothing for you to do here. It computes this additional resistance to flow due to the particle-to-particle impact using this relationship from this plotted data in this previous table. So again, I used the exponential relationship. So at high particle concentration, dispersive stress transfers more momentum to the boundary by particle-to-particle contact. And this is all hardwired in the model, so you don't have to do anything. Now, what you should do now to begin your modeling process is consider that you have a water hydrograph, and that's this blue line here. And if you have some sediment that's approaching like a typical mud flow, where the concentrations are on the order of 45 to 50% concentration by volume, these typically occur on the rising limb of the water hydrograph, and then the recessional limb, it becomes more dilute. This is if you have a hydrologic event occurring. So in this case here, we have this concentration by volume, and it gives rise to the mud flow event, the black line here. You can see it's highly bulked up to a discharge, in this case of around 300 CFS, where the original hydrograph, if you just modeled water, was only on the order of 150. Then if you propagate this downstream to the, say, the fan terminus or something like that, and what would happen is that you can see that the timing here, the peak occurs at around 0.6. Here the peak is occurring around 0.7 or so with the water event, but the peak is more delayed with the mud flow event, and you get this much more elevated type of event as the hydrograph compresses, and so you get the peak catching up with the frontal wave. This becomes very steep and so forth. So this is the bulked hydrograph somewhere further down on the fan compared to the water hydrograph. So to conduct now a mud flow simulation in Flow 2D, what you have to do is switch on the mud switch in the control.data file. Turn off the sediment transport switch, the conventional sediment transport, where you're going to select the sediment transport capacity equation. And if you were just bulking the flow without modeling a mud flow or sediment transport, you could use the X concentration factor, say 30% or 20%, and that would just bulk the entire flow for you. If you're just doing a bridge design or something, you could do this because you want to make sure you account for the sediment. Otherwise, you're under designing your bridge for the 100-year event, and especially if the concentration can get up to 10 to 20% concentration by volume. At 20% concentration by volume, you're somewhere on the order of about 25% bulking factor or 125% bulking factor. So that's important. But you turn both of these off in the cont.data file if you're going to model the mud flow event. Then you have to add one line in sed.data. And these are the coefficients and exponents for the viscosity and yield stress. So here's from that table, This is Glenwood number 4. I'll go back through this for you. Whoops. Here it is. Sorry. So this is Glenwood number 4. You can see this is 0.00602 and 33.1. We just remember those two numbers. And you come up here to this, oops, sorry, M line, just the M line and said dot data. So I call this table 9, and it's from this Mudflow simulation guidelines, which you can download from the website. And here's the Mudflow coefficient and exponent, the yield stress coefficient and exponent, a specific weight. This just allows you to go from 2.65, which is typical for sand, up to something that's more of a, has more clay in it, like 2.74 or something a little less maybe. And then you can enter the K factor laminar flow resistance coefficient here. And if you set that equal to 0, it computes it directly from Manning's N. So now the only other thing you need to do, so that's fairly simple so far. You select one of these concentration by volume and exponents and coefficients, and you're almost ready to go. You need to have a concentration in your inflow.data file hydrograph. So here's the data file for inflow.data. Here's the hydrograph. It's going to have inflow to the floodplain. It's going to come in grid element number 48, 486. It's part of the hydrograph. There's time and water discharge. So if this is your 100-year water event, if you turn off the the switch for mud equal to 1 and leave off the constant, or even if you have the concentration by volumes, it will just run this as a water event, and you can model the water event. Now, if you put in all 45 or 50% concentration by volumes here, you'll model this as a sole uniform concentration by volume for the entire event, which may be some appropriate for that removal of the log mill in that movie that I showed you before. That was pretty uniform. It got a little bit more fluid towards the end, but something around 45, 50%, depending on using which of the samples you used from table 9. And I would use, if you wanted to model that mud flow event with the where it removed the log mill, I would definitely consider the Glenwood sample number 4. That's this one right here, because it behaves like wet cement, and that's from my experience with it. So now, how do you distribute this concentration throughout the hydrograph? Well, you want to start somewhere around conventional water, because as you saw with the water going over that dam in the mud flood movie, that was probably around 20% concentration by volume. Then it rapidly increases on the rising limb. Probably by the time it gets to the peak, it's starting to decrease a little bit, and then it decreases down to where the recessional limb is once again very fluid, but still carrying a lot of sediment, 20 to 25% concentration by volume. We're going to compare all of this next week in terms of how we distribute this concentration by volume, so that we can match the supply with what the model is predicting in terms of the sediment volume. And so this will all make sense to us next week. And the way that we're going to do this is we're going to go to the summary.out file, where the water and the bulked with sediment is reported. Now above this, it shows that it shows the time step, the output interval, volume conservation columns up here, and then this is the end of the summary.out file, and this shows the ultimate disposition of the water and the sediment. And these are not important. You don't have to consider this. Just the bulked with sediment is all that's really important here. And you can see here that the total volume of outflow plus storage is equal to 36.73 acre feet in this case. You can, if you're doing it in metrics, it would be cubic meters, but it's equal to the inflow hydrograph, which is bulked. So how much sediment is in this? Well, if you subtract the water from the bulked with sediment, it's 14.04 acre feet. If you divide the 14 acre feet by the total here, which is 36, the concentration is around 35%. And that's what you need in order to have a mud flow event. If it's less than around 25 to 35% concentration by volume, you can't have a mud flow event at all. It's going to be totally fluid throughout the entire event because the peak will just catch up with the frontal wave and dilute it. And the frontal wave might slow it down till a point where it gets near the fan apex, but after that, it's all mud flood. So if you don't have this in a relative range of 30% concentration by volume or higher, you're not going to have a mud flow event. So there's one more way to add this sediment volume to your inflow hydrograph. And that is, instead of adding the concentrations here, if you had an actual landslide event occur and you wanted to dump this in with a hydrograph of water, you can do it in terms of the actual volume, cubic meters or cubic feet, whatever you wanted here. And you know, if you have an aerial photograph and you go out in the field and you see that this landslide occurred and it's roughly taken off about 3 to 5 feet for, say, 500 foot long by 300 foot wide, you could estimate the volume and just distribute that volume into this hydrograph, and you'll do it the same way. When you run it, you'll subtract these two values and this will be the total for you, and that should be equal to the 5 foot of depth times 100 foot width times 500 foot length, and adjust for the porosity because this is a solid volume here. So you want to make sure you do the ground to solid volume adjustment factor, which is porosity of 40%. So now that I've got you to this point, you might say, okay, you've given me a whole range of different possibilities. How am I going to possibly entertain which flooding scenarios to use? Well, this is what I would do. I would do a water flood event, first of all, and then I would add the X concentration factor and CONDOT data, and that could be like 30 or 40% concentration by volume, or maybe just 20% concentration by volume. Typically, that's a good amount for like a 100-year event or something like that. And this would just give you a bulked flow event that is just going to be fluid. So you can compare this bulked fluid with the water volume. Then you go on to the mud flow events. So this is going to have a variable concentration. Typically, for most hydrologic initiated mud flow events, they're going to have a recurrence interval on the order of the 10 to 25 year event. The 100-year event is going to be too fluid. And the reason for this is if you go up in the watershed and you try to estimate the amount of sediment coming off, there's no way that you're going to get 30% to 35% average concentration throughout the entire hydrograph in terms of sediment. The peak discharge and the volume for the 100-year event has way too much water in it to do a mud flow event. So these typically are on the order of a 10 to 25 year type of hydrograph, might be even slightly smaller than that. And that's because that's the interval that it takes for the channels and the watershed to recharge itself in the channel in order to generate a mud flow event for the next 10 to 25 year event. Now, we also want to look at different types of urban features if you're going to do this flooding down into your city or community. So these are important hazard events to consider here. I'll give you a very simple example of one. This is Centerville, Utah. I think they built an actual mud debris flow basin in here at some point. They used to have a little detention basin here, which didn't store anything, and it not even a percent or two of the 10-year event. So this comes down, the frontal wave hits it, puts a little debris in it, it just overtops it, runs down the street, gets in amongst the houses, and comes down here, down this street pretty quickly, and smacks right into this school building. So you can see this street's really steep. It's on the order of 7 to 10% slope. So it roars down this, any mud or debris flow event or mud flood event will come down this street fairly quickly. So I'm going to show you this simulation. There are very steep slopes. There's a very small debris basin that I let fill at the fan apex first and then come over. There's street flow conveyances. Some of the buildings help to keep the flooding confined to the street. And then I'll show you what happens if you do water, flood, and rain. So hopefully this will just run for us. Yes. So again, this is a very simple one, 100-foot grid elements here, just to give you an idea. You can see that it's very high flow depths on the order of 5 feet and higher initially, and the mud flow is stopping after just an hour or less, or whatever it was I ran it for. I forgot to look. And you can see that the mud flow piled up to the order of 3 to 5 feet in front of the school building. Most of it was confined to the street along the main avenue. The debris basin was located up here at the top. I stored a little bit of the initial frontal wave in it. So now let's look at what happens if we just run it as water, not bulked at all. We're just going to run it as water, and we're going to leave the streets in it. Conserving volume. Here's about a 2-hour total event. And you can see that the streets are actually helpful in confining everything except for the peak flow event. And we have nothing but shallow depths on the order of a half a foot. So we might have a slightly larger area of maximum area of inundation than the mud flow event, but obviously the mud flow event has very high flow depths if we plotted the maximum flow depths here. And this is just simple graphics, but you could graph all of this in Crayfish and in QGIS, and Karen might show you how to do this in one more webinar after I finish the 4th one here in a couple of weeks. Now, this is interesting here. Watch what happens if you take the streets out, leave the buildings. So here comes the mud flow again. Now look at, the mud flow is catching up with the frontal wave, and it's going to cease flowing essentially right here. And it created all these frontal berms and deposits and so forth. So the deepest depths are in the frontal wave. And so that was kind of interesting. And the streets are very important in terms of sending the mud flood or mud flow down to the school building. Now, let's see what happens if we actually combine the storm that generates the mud flow. So it's raining now, it's raining on the fan here on the urban area. Here comes all the rain. Now here comes the mud flow. So the water is adding to this on the fan, and it's diluting it. And so we're getting smaller depths in front of the school building here. And you can see that the flooding's a little bit more widely dispersed because the event's more fluidized, and it flowed much further down than the initial run, which was located in and around the front of the school building. So that's kind of a simple thing, but it just goes to show you how important features are, and to include, things like rainfall on your mud flow events and so forth, because these don't happen in isolation. you got rainfall occurring, and maybe the rainfall is moving up into the basin, or maybe it's in the basin and moving downstream. Now, if we were to move on to two-phase flow, which we'll do in 2 weeks from now, I'll show you some results of how the mud flow and mud flood might function with a tailings dam breach failure. Here's the tailings dam, stored it. There was water on the surface. It breaches, the water and mud flow continued downstream. This is maximum depths for water and mud flow. But if we separate these, here's the fluid event coming down. This is all modeled as a single event, not two different events. This is a single event. So this was the fluid depth. You can see it's deeper near the dam face here. So this is the fluid surface here on it. And then the mud flow event, when it started flowing here, this is the tailings material that moved out of the tailings reservoir and moved on downstream, and how much of this was somewhat scoured away by the event. So there was some interchange between the fluid and mud flow layers, and between the fluid and the bed layers in terms of scouring the sediment downstream. So this mud flow is ceased flowing. Yes, it has it. You might ask the question, is this the final? This is the final mud flow depth. This is after 24 hours. This is the mud flow velocity. There's a couple of elements that are still just oozing around, as is typically the case with a mud flow event, which you can see here, but the mud flow has ceased flowing. And some of the higher concentrations are still remaining and behind the event. So this is actually predicting the drainage. Now, one final note is, if you wanted to do building collapse in front of your mud flow, you can do building collapse by creating vulnerability curves or entering some vulnerability curves. So you could have a good building, a moderate building, or a poorly constructed building. And across the line is where, in a plot of velocity versus depth, will be where the building gets washed downstream, just like those shelters in the log mill were destroyed, and so forth. This is the same concept here. So I wanted to, this was requested by some researchers in Italy. I put this into the model for them, and you could do this with mud and debris flows as well as water. Okay, so that's the end of my presentation. Next week, we're going to do mud flow sediment supply and show you how to match the volumes up so that the simulations make the most sense for you. Now, let me just remark that once again, that it is possible for us to come and do training, not only for mud debris flows, but for the entire model at your location. We haven't been doing these for a while. We used to do them every year for the Floodplain Management Association and for the ASDSO and for others organizations, but we do them around the world for other government or even private entities. We've done these in like 20 or 30 countries. We've done about 50 of them in various sites around the world. Typically, the price range is on the order of 10 to 20,000, depending on the number of people and the cost of flying to your location. But if you wanted to have a training class, we're entertaining reservations. Again, we haven't done these in a couple of years because of COVID. So if you wanted to do this in your country or in your city, if you have opportunities to book or have a venue for 20 or 30 people or more, we'd be glad to do it. And if you wanted to put one of these training classes on, they typically take 3 to 5 days, depending on how many components you want to look at. They're all hands-on. Karen and Noemi and others that we might bring do a very good job in allowing you to do it on your own computer and So we're happy to do these. We like doing them, and that's a consideration for starting in the summer, I think would be a good time.